let's get started. We are talking about, actually, let me pause here and say that I know registration is happening soon, so some of you guys have been asking me about research. So I do research, and if you'd like to, you can do research with me in the fall for anywhere between 1 to 3 units. 1 unit would be about 3 hours of work a week, and that work would be in the lab or on the computer or whatever assignment you have for that week. But you can do research with any professor that you like. It's always good to do research, even if your degree doesn't require research. It's good for you to do it. But for my research, I do synthetic organic chemistry. So basically making different compounds, so doing organic reactions to make different compounds to test them to see if they're active against different diseases. So I make pharmaceuticals, but there's lots of different research projects going on campus, so make sure that you talk to some of your professors to find out what they're doing and see if they have space for you. But just a plug, at the end of the month, there will be the NMS Research Symposium, and it'll be virtual, but on that last Saturday of the month, you can go, you can attend it, and you can find out about what all the professors are doing, because the students will be presenting on what they've been working on for the past year or so. So keep that in mind. Was it March 27th, I believe, at 9 a.m. So you'll get emails about it. And you've probably been getting emails about submitting an abstract, but that'll be a good way for you to find out about other people's research. All right, so we are talking about these conjugated dienes, right? We have this 4-carbon chain where we have these 2 alkenes. And so we know that we have 4 carbon atoms, and each atom would bring its own atomic orbital. So that means we have 4 atomic orbitals, right? And so if we take these 4 atomic orbitals and we mix them to get 4 molecular orbitals, then here are our molecular orbitals, right? We have 2 bonding molecular orbitals, and we end up with 2 antibonding molecular orbitals. So the 2 bonding molecular orbitals, we have no node or 1 node, and then we have the 2 antibonding where we have 2 and 3 nodes. But as we make these, as we mix these together and get these molecular orbitals, how many pi electrons do we have? Remember, we have 2 and we have 2, so we have a total of 4 pi electrons. And so with these 4 pi electrons, where do they go? They only go into bonding molecular orbitals. There are no electrons in our antibonding. So the energy to begin with for our atomic orbital would be here in the middle. And so we've lowered the energy overall for the bonding molecular orbitals, putting electrons in there. Instead of those 4 electrons being in atomic orbitals, that would be energy right here in the middle. We have lowered them overall, which is why this conjugated diene system is more stable than the other kinds of systems that are non-conjugated. Questions on that? All right, so now this is 14-6, looking at some of the reactions that we could do. So the same reactions that we could do with the alkene, we can do those same reactions here with the diene, with the conjugated diene. So the same reactions we were looking at in chapter 12, we're looking at them here, but in a slightly different way. So here we have our diene, 1,4-butadiene, and we add an HBr. So we know with HBr, we have a partial negative, partial positive. We have electron density between the 2 carbons. So from the middle of the bond, we got hydrogen, and we break that bond. We know that that's going to happen. We know that that's the reaction that occurs. And so with that reaction, let me number these carbons. We're looking at, where does that hydrogen go? Does the hydrogen go to carbon 1, or does the hydrogen go to carbon 2? So that's what they are exploring here. If the hydrogen goes to carbon 1, we end up with this carbocation on carbon 2. But if the hydrogen goes to carbon 2, then we have a carbocation on carbon 1. Right? We have these two carbons where the hydrogen can go. So where does the hydrogen go? Well, we know from last chapter, from chapter 12 rather, we know that this addition follows Markovnikov. And so if it follows Markovnikov, we know H goes where there are more H's. And so here, that's even more important. So for this, if we were going to have the hydrogen go to carbon 1, then we would end up, so attack at carbon 1, we'd end up with this secondary carbocation. Versus if we have the hydrogen add to carbon 2, so you see here attack at carbon 2, we end up with this carbocation. Now, what's the difference in the two? Yes, one is primary, one is secondary. But even beyond that, so this is primary, which is bad, but it's also non-delocalized. There's no way for us to stabilize that by resonance. Non-delocalized positive charge. There's no way for us to stabilize that by resonance. But here, if we put the positive charge on carbon 2, look at that. Now we've made an allylic carbocation. And what do we know about those? We can delocalize that. It's stabilized by resonance. So here we know that this is what will form, not this where we have this non-delocalized positive charge. We know it because of Markovnikov addition. And based on Markovnikov addition, we know that we're going to get this secondary carbocation that is then stabilized by resonance. So Markovnikov, H goes where there are more H's. We know that there are 2 H's here and only 1 H here. So H goes where there are more H's. The hydrogen adds to carbon 1 here. So with this reaction now, so we said we're going to make this carbocation in our first step, right? We go and pick up a proton and we break this bond. This is from the last slide. And so we said we're going to have this carbocation that's on carbon 2. And we do that because it's stabilized by resonance, where we can, from the middle of this bond into the middle of the bond, move those electrons over, where now we have a positive charge on carbon 4. Remember, we don't move around the atoms. All we can do for resonance is move around the electrons, which moves around the charge. So we have these 2 carbocations here. With those, something has to have a negative charge. What would have a negative charge? Well, remember this arrow that we drew here? We're going to be with our bromide as the counter ion for both of these. And so we can have bromide attack either carbocation. Here, I'll just draw the arrow to this one where we have it on carbon 4, but you know it can also attack carbon 2 for the other carbocation. Both of those are the same. And so we end up with these 2 products. So one product where we have added our bromine here, and one product where we've added our bromine here. These are the same carbons, carbons 1, 2, 3, and 4, but where the bonds are, that is what has changed. So we can either have the bromine added to carbon 2 or the bromine added to carbon 4. Now remember, initially we added in a hydrogen. That was our first step, right? And we said that H goes where there are more H's. We said there are 2 hydrogens here versus only 1 hydrogen here. And so we know that we added in that blue hydrogen. We know we added it on carbon 1. So I'm just going to add it in. We don't have to show it, but I'm just showing you it here so that you can see what we're about to do. So if we add that on carbon 1, then hopefully you can see that we added the hydrogen to carbon 1 and the bromine to carbon 2. So we would call this a 1,2 addition. Whereas here we added the hydrogen to carbon 1 and the bromine to carbon 4. And so this would be called a 1,4 addition. So we have our 1,2 addition and we have our 1,4 addition. 2 different ways of adding the hydrogen and the bromine of HBr. Our hydrogen is our electrophile, bromine is our nucleophile. And so we can get these 2 different products from our allylic carbocation. 2 products are possible. Because the 2 sides of this are different from one another, these 2 carbocations are different from one another, we end up with 2 products formed here. Questions here? So that's one type of reaction that we can do. We've already seen this before, step 1 of it, at least, adding a hydrogen to the double bond. And so we've already seen this 1,2 addition, right? The 1,2 addition is what we were doing before, back in chapter 12. But now we're seeing that because this is conjugated, we can also do a 1,4 addition. So we have 2 different products that are formed here. Now we'll talk about these yields in a minute. But let's talk about one other thing really fast. With this reaction, we can do other kinds of electrophiles and nucleophiles. So we know here, if this is partial positive, this is partial negative, we know that this can be our electrophile. We've seen this reaction before, right? And this is our nucleophile in the solvent carbon tetrachloride. We saw this reaction in chapter 12. So what did we say in chapter 12? In chapter 12, we had, let's say, this alkene, and we added in bromine in carbon tetrachloride. And so we said for this reaction, we're going to be making this bromonium ion. Two lone pairs on the bromine, full positive charge. So what were the arrows for that? Well, we have Br, Br. One of those has a partial positive, one is a partial negative. Let me show my lone pairs, because we know we're going to attack the electrophile, break the bond, and then bring in this third arrow to one of the carbons, right? That's from chapter 12. This is review. You should already know this. And we know that there'd be some stereochemistry here on this methyl. That's where we would show the stereochemistry. I'm not going to show it here, but we know we would get this product, not this product. What's the difference here? So let me number these. So 1, 2, 3, 1, 2, 3, 1, 2, 3. What did we say was the difference here? Well, we said that we weren't going to form this because here we have a sextet of electrons, whereas here we have all octets. Every atom, even the bromine, has an octet of electrons. So that's what we said. We said we were going to form the bromonium ion because we get all octets instead of a sextet. But here, now we're seeing that in this chapter, the same exact reaction, same reaction. We're going to attack the bromine, and we're going to have this bond break. Basically, we're not going to do that third arrow. So we are going to form this with this carbocation here, and not this. What's the difference here? Well, remember the difference is that we have this double bond. So the difference here is that with this double bond, we're going to form this, even though it has a sextet, because this can be stabilized by resonance. This carbocation cannot be stabilized by resonance. There's no resonance that you can do there. And so that's going to be very unstable. So we go with the one that has all octets. But now in the second case, because it is a conjugated diene, we're going to make this carbocation that is stabilized by resonance and not the bromonium ion, because that's not stabilized by resonance. So we have these two things that have a positive charge, but only one is stabilized by resonance, so that's what we go with. So here in this reaction, we end up with these two resonance forms. Actually, let me do it up here. So as I've shown you, we have this positive charge here on carbon 2, and we can, from the middle of the bond into the middle of the bond, draw this other resonance form where we end up with a positive charge on the other end. So we have these two resonance forms that are possible. We know that we have bromide hanging around. Where'd the bromide come from? Remember this arrow over here where the bromide leaves? So we have bromide hanging around. Bromide can attack either of these carbocations, so I'll just draw the arrow over there. And so we end up with these two products possible. So they've shown you the products here, but let me draw them out for you also. We have this product, and we have this product. We can't end on something with a positive charge. We want to end with something neutral. So here are the two products that we can form. What's the difference between the two? Well, this is the 1,2 addition, and this is our 1,4 addition. So we get these two different products formed here. Questions on this? So we're applying the reactions that we saw before in chapter 12. We're applying them to now this conjugated diene system and seeing how resonance now will allow for more potential products. And again, this is different from hydride shifts. Hydride shifts and resonance are two different concepts. So let's go back to our original example there with the HBr. Remember I said we would talk about those yields, so 70% yield and 30% yield. If we keep the temperature low, then this would be our product distribution, where we'll get more of the 3-bromo-1-butene than the 1-bromo-2-butene. But if we increase the temperature to 40, so let's just say higher temperature, it's not really that high, but a higher temperature, then we change it. Instead of having 70%, now we have only 15%, of the 1,2 product and 85% of the 1,4, just with heating it up to 40 degrees. If we take this product mixture where we have 70 and 30 and we heat it up to 40 degrees, we're going to make this product mixture that's 15 and 85. Heating the product mixture from 0 to 40 will also change it. Even though you have 70% of one thing, 30% of the other, if you heat up that 70-30 mix, it will end up being the 85-15 mix. Or if you start off running the reaction at 40 degrees, you're going to end up with this 85-15 mix where you get more of this product that would have been unfavored at lower temperatures. So what is happening here? Well, we're seeing that at higher temperatures, these isomers are going to be in equilibrium, so we're going to get whichever product is more stable based on thermodynamics. So remember what thermodynamics is? That's not our rate. That's talking about what's lower energy. What's the more stable product? And so look at the two products. We have a terminal alkene versus an internal. And so at higher temperatures, we're going to see more of the product that is more stable. We know the internal alkene is more stable, and so we're going to make the product that's more stable based on thermodynamics. And so what did we say before? We saw this before in chapter 12. Remember in chapter 12, we talked about dehydration. We talked about kinetic control and thermodynamic control with the dehydration. Same concept. Here at higher temperatures, the thermodynamic product is favored, so we would say this reaction is under thermodynamic control. The ratio of products is going to reflect the thermodynamic stability of the product's form. The more stable product will be what will be favored at higher temperatures. So then what's happening at lower temperatures? At low temperatures, we have our isomers not interconverting. So we're talking about the major product is just going to be whatever's formed fastest. So what is fastest? We know that that's kinetics now. The rate of the reaction, we're talking about kinetics. So whatever's formed fastest, that's what we get the most of. So this is what's formed fastest, which is why we have a higher yield of this. Why would this be formed fastest though? Well, what is this formed from? The 3-bromo-1-butene. The 3-bromo-1-butene is formed from this carbocation versus the 1-bromo-2-butene is formed from this carbocation. What's the difference in the two? Why would this one be formed fastest? Well, it goes through the secondary carbocation versus here where we'd have to go through the primary carbocation. We know that for stability, this is more stable. We know our secondary carbocation is more stable, lower energy intermediate. And so we're going to go with what's formed fastest here, which is going to be whatever's the most stable carbocation intermediate. So this is under kinetic control at low temperatures. So kinetic control at low temperatures, thermodynamic control at higher temperatures, low temps based on the carbocation stability, high temperatures based on stability of the alkene product. So what does this look like? When we are looking at this reaction, here is our resonance hybrid. So for our resonance hybrid, that's going to be our intermediate, right? We've protonated, and as we protonate, we end up with this positive charge where it could either be this primary or this secondary carbocation, either one. So which one are we going to go through? Well, if we go through our secondary carbocation, and that's going to be lower energy than trying to go through our primary. And so look at the difference in energy of the transition states. What's easier to do? Well, it's easier for us to go here to this lower energy hump, right? We don't have to put in as much energy to get over that mountain versus trying to go here and go over this mountain. That's going to require more energy, and so it's going to be a slower reaction, whereas this is a faster reaction because we're going through this secondary carbocation. So initially, if we keep this at low temperatures, then the fastest reaction will be whatever has the lowest energy transition state. So the fastest has the lowest energy transition state. And so our lowest energy transition state, look at the difference in energy of the products. We're going to get the less stable product, but it had the lowest energy transition state. So at low temperatures, we would make this. We make the higher energy product, but because we're going through the lower energy transition state. So that's at low temperatures. But if we heat it up, remember, as you heat things up, now you have things hitting each other, that now everything is going to have more energy. And so as you heat things up, everything has energy. Now we can get over this barrier that was maybe a bit too high at low temperatures. At higher temperatures, now we'll have enough energy to get over this higher energy transition state. So even though it's a higher energy transition state, now the molecules will have more energy, so we can go through this higher energy transition state through a primary carbocation and get down here to our more stable product. So at high temperatures, now we can easily go from here back up, we can go up over this barrier, and we can get back down here to where we need to be at the lower energy product. So that's why we can take a mixture where we have more of this. So we said 70% of this at low temps. If we heat that up, that 70% changes into only 15% because more of these molecules will change back into the carbocation. We'll go from the secondary to the primary carbocation, and then we'll go over here to form product at higher temperatures. Heat it up, things start moving, we can break some bonds, get this carbocation back, and we can go all the way over to the more stable product. Questions there?
Yeah, does that only apply for brominations?
This only applies for this system where we have an allylic carbocation that we can stabilize by resonance. So for this reaction, this HBr, and for that the bromine reaction, yeah, this applies to it.
Quick question, Professor. So, since we talked about temperature and the cold, I didn't see any like mention of alcohol. So, will alcohol not play an effect at all? Because, like, I remember from like chapter 12, we were making alcohol in.
Well, that was that reaction. We were talking about a dehydration reaction there. And
Okay.
so that mattered for that reaction. Here, we're not talking about alcohols. We're not talking about hydration or dehydration. But in chapter 12, we were talking about hydration, dehydration, going back and forth, where we could go back and forth and get the most stable alkene product. Here, we're not talking about that reaction. We're talking about what happens when we add in HBr or when we add in bromine at low temperatures. Then it's going to matter about the carbocation. At high temperatures, the stability of the product will matter. So we said at low temperatures, we're going to favor the less stable product. And this is because the carbocation that we make is asymmetric. So we know we have this carbocation, and so based on what they have here, I'm going to draw it two different ways. We have this two different carbocations here. So this would be our methyl. So if I number this, 1, 2, 3, 4. 1, 2, 3, 4. Here's carbon 1, carbon 2, 3, and 4. So what do we see about those carbons? Well, looking at them, we can see we have these areas of low electron density, right? Where we see purple, purplish blue, that is low electron density. That's where we have the positive charge. We know the positive charge is on carbon 2 and on carbon 4, and we can see that it's delocalized. We've delocalized that positive charge. It's not just on 2 or just on 4. It's delocalized over 2, 3, and 4. But where do we see more positive charge here? More positive charge is going to end up here. Sorry, I did this numbering backwards. I did it based on what we were doing before. So let me change this numbering so that it matches what's on the slide. So based on what's written on this slide, we have here 1, 2, 3, 4. And so we can see here that we have more positive charge building up on carbon 3. And so here we see this, a lot of blue here on carbon 3 versus carbon 4, not as much, carbon 1, not as much. So we have more positive charge building up on that secondary instead of that primary. So the positive charge is unequally distributed. More positive charge on the secondary than on the primary. So here we can see what's happening there with it being that secondary carbocation. We can see why we would do the 1,3 addition versus the 1,4 addition in this reaction, based on the lower temperatures, I should say. Questions on that? All right, moving on now, 14-7. So we talked about allylic systems, one double bond. We talked about our conjugated diene. Now we can have extended pi systems, even more extended, where we have more than 2 double bonds in conjugation. They have to be in conjugation, double, single, double, single, double, but that's an extended pi system. So here we have 1,3,5 hexa triene, 3 double bonds, 1, 2, 3, 4, 5, 6. So you can see why it's called 1,3,5 hexa triene. So this compound is very reactive, and it will polymerize easily. What's our polymerization? We know that that's where we have the alkene reacting with itself. So numerous of these 1,3,5 hexatriene molecules can react with one another, or we can polymerize. So it's very, very reactive. But with it being reactive, it's also stable. That's weird. Usually, if something is reactive, it is unstable. But this is both stable and reactive. These are very interesting systems. Both stable, you'd think that'd be very unreactive, but it is stable, low energy, but also reactive. So we can do the same kind of reactions we were just looking at for the diene. Those apply to the triene, so those electrophilic addition reactions that we saw in chapter 12, they also apply here. And so with this, we have 1,3,5 hexatriene. We've added in bromine. When we add in bromine, we're going to add it to carbon 1. Why are we adding it to carbon 1? It's a Markovnikov addition. What did we say, H? Or the electrophile added where there are more H's. So you have this whole chain. The only place that it could add, where are there more H's, either 1 or 6, doesn't matter, those are the same, right? Carbon 1 and carbon 6 are the exact same. So here they're just going to add the electrophile to carbon 1, but it would have been the exact same thing if you had added it to carbon 6 in this case, so it didn't matter. But if we add that to carbon 1, then we know carbon 2 would be the carbocation. And we know that we could draw a resonance form where now we get a double bond between 2 and 3, and carbon 4 becomes the carbocation. And then we can draw another resonance form where now we have carbon 6 as the carbocation, and we have now 2 double bonds between 2 and 3 and between 4 and 5. So we have these 3 resonance forms. We've stabilized this carbocation with these 3 resonance forms. More resonance forms means more stable. If you can draw more resonance forms for an intermediate, that makes that intermediate even more stable. The more resonance forms you can draw, the more stable that intermediate is. Stabilized by resonance. So we have this reaction that we can do. We can easily do this first step. Low activation barrier. What does that mean? Low activation energy. So we can easily form this carbocation intermediate. They're all stabilized by resonance. So we get these 3 products. The 1,2 product, the 1,4, and the 1,6, because we know we have bromide hanging around. They can attack any of those carbocations. So we can attack carbon 2, carbon 4, or carbon 6. So we get these 3 products formed here. Which one of these products do you think would be the most stable product? So either put 2, 4, or 6 for the 1,2, the 1,4, or the 1,6. Which one of these products do you think would be the most stable product? So either put 2, 4, or 6 into the chat to say the 1,2, the 1,4, or the 1,6. The most stable product is this. Why is this the most stable product? Because we have these 2 internal and conjugated alkenes. 1,6 is going to be major because we have 2 internal and conjugated alkenes for the product. What do we have here? Yes, these are conjugated, but we have 1 terminal. Here, these are non-conjugated. We have this double, single, single, double. For the 1,4, we have a double bond, and then we have a single bond, and then a double bond. So it's non-conjugated. So this is major because it's 2 internal and it is conjugated. Questions on this? Again, remember our solvent here, carbon tetrachloride. And remember, we're not forming the bromonium. Why aren't we forming that? Because we can make a carbocation that is stabilized by resonance. So with these extended pi systems, a lot of them exist in nature. So we've seen one. We already saw beta-carotene at the very beginning of this chapter. And we said that beta-carotene is responsible for that orange color that we see for carrots. So if you eat beta-carotene, this will turn into retinol or vitamin A in the body. But both of these compounds are very reactive to electrophilic addition reactions because we have this extended pi system. Look at all this conjugation here. We have this extended pi system, all these double bonds in conjugation, so we can make a bunch of different resonance forms. Imagine how many resonance forms you can make for beta-carotene if you added a proton to one of these ends of the chain. So here's another extended pi system, benzene. So we've seen benzene before. And so what have we been saying? We've been saying that we have these extended pi systems. They are very reactive, but very stable. Benzene is not very reactive. much less reactive than other extended pi systems. But it is that way because it is a cyclic conjugated system. So benzene is in a class all its own. We're going to have 2 chapters devoted to benzene on its own. But we know that benzene looks like this, where we can draw the other resonance form by moving these electrons around, right? And then we can get back to our original resonance form by moving the electrons in this way. For benzene, all these electrons are conjugated, right? We have all this conjugated, these conjugated double bonds in benzene, and we can move them around in this circular manner, around and around and around and around and around, based on resonance. And so we usually will just draw it as this circle, saying that we have those 6 pi electrons that are all in conjugation with one another. They're all in conjugation. They are all, they have these different resonance forms. So these 2 resonance forms, these are equal. Two equally contributing resonance forms. We've delocalized these electrons all around the ring. This is what makes benzene so stable and unreactive. So it's unreactive. So it is stable based on thermodynamics, so low energy, and it's stable based on kinetics. The rate is low. If we're going to do a reaction, it is an extremely slow reaction unless it's one of the specific reactions that we know of. It's not going to do the regular alkene reaction. So osmium tetroxide, no reaction. Try to add in bromine, no reaction. Try to do a hydration reaction, no reaction. It will not do the regular alkene reactions because of this stabilization, this resonance stabilization where we've delocalized all these electrons in this ring. If we try to do the hydrogenation, it could happen, but it's extremely slow. Remember, that's talking about kinetics. So this is something that's very stable based on thermodynamics and kinetics. It's not going to want to do any of these reactions. So it's different from the other extended pi systems. Benzene is in a class all its own. It is stable thermodynamically and kinetically. We're going to see only a few reactions that it can do. We'll look at that in the next chapter and the chapter after that. But we did see our extended pi systems are very reactive. Let's see. I don't really know what you're asking, Valerie, about purple carrots or something. I'm not really sure what you're talking about.
It's because
I think that would be a really great thing for you to tell us all about on Monday after you research that. So go ahead and you'll unmute yourself on Monday and you can tell us all about that. But let me tell you about this. This might help you a little bit with what you're asking, but feel free to do deep research on whatever it is that you are talking about with carrots originally being purple or something. I have no idea about that, but I look forward to you telling me all about it. But anyway, 14-11, we have this type of spectroscopy that we're going to look at. So again, Valerie, this might be answering your question or it might not, I'm not sure. But anyway, so we know that white light is going to be a full spectrum of color after it goes through a prism, right? We know that, we get that rainbow. So when we see an object that's colored, we know that it is absorbing light and reflecting some colors toward our eyes. So if it absorbs blue light, it appears orange. If it absorbs orange, it appears blue. Absorbs purple, appears green. You know about that already, I'm assuming. So in organic chemistry, we have these compounds that can have a color. So you know a lot of things that we've seen have been colorless compounds, but sometimes they have had a color. So remember when we were doing our trityl methyl ether, you guys had that bright red color, and then it changed colors when you added it to the methanol. So that's based on what we're talking about here. So when a compound has color, It's usually because it has these conjugated double bonds. Conjugated double bonds, beta carotene, all these conjugated double bonds, that's how we see this orange color. Indigo for blue genes, it has this extended pi system. The nitrogen has these lone pairs that are also involved in this extended pi system. But we have all these pi electrons that can be delocalized. That gives us the blue color of indigo that will dye blue genes. So these organic compounds have these extended conjugated pi systems that gives it its color. So what is happening there? Well, we have these electrons in the molecule, right? And so for the molecule, we have some electrons there. And for the electrons, they are going to be in bonding molecular orbitals, right? We discussed that. These pi orbitals, bonding molecular orbitals, and then we said we have nothing in the anti-bonding molecular orbitals for these extended pi systems. So there are more electrons there. They're just showing you at the topmost bonding molecular orbital, and then they're showing you the lowermost anti-bonding molecular orbital, but there are more pi orbitals above and below what you see down here. So we have this difference in energy, so delta E, difference in energy between our bonding molecular orbital energy and our anti-bonding molecular orbital. If we shine light on this molecule, light, or H nu, is going to have some energy, right? Light has energy. And so if we shine light, let's say UV light, 200 to 400 nanometers, or visible light, 400 to 800, then that light can have energy that's equal to the change in energy between these two orbitals. If it has the right energy, if the change in energy is equal to the energy of the light, then we can take one electron and excite it up. So we can take this pink electron and move it up to this antibonding molecular orbital, getting us from our ground state to the excited state. Shine light on something, an electron will pop up, we'll get to this excited state. If you shine light on that and it doesn't have the right energy, then you can't excite up an electron. But if you have enough energy there, that is the same energy difference between these two orbitals, then you can excite up an electron. So we can see these different, we can quantify rather, I should say, the color by using spectroscopy. So we're talking about UV vis spectroscopy using UV light and visible light, to see the conjugation of these different molecules. So let me tell you some terminology that is used in other textbooks, or maybe on the MCAT or something like that. So we have what's called the HOMO and the LUMO. So the HOMO is the highest occupied molecular orbital. And then we have the LUMO. That's the lowest unoccupied molecular orbital. So we have the HOMO and the LUMO. When we shine light on the molecule, then this now becomes the HOMO, and whatever the orbital was, whatever the pi orbital was above that, that now becomes the LUMO. So we're changing our HOMO and LUMO there. We don't use that terminology in this textbook, so I'm not really going to refer to it in that way, but just know that that is the terminology. If you are looking this up or reading about this somewhere else, that's what they're talking about. The highest occupied and the lowest unoccupied molecular orbital. All right, so how do we do this UV vis spectroscopy? So we take an organic compound and we dissolve it in a solvent that does not absorb UV or visible light. So we would use methanol or ethanol. So why won't the solvent absorb UV or visible light? Well, for the solvent, it's going to have really only sigma bonds. But for our organic compounds, those are going to have pi bonds. That's what we're looking at, right? Those double bonds in conjugation. And so for sigma bonds, this difference in energy, this delta E, between the bonding and anti-bonding molecular orbitals, that difference in energy is too large. It's too large for UV or visible light to excite the electrons. That change in energy is too large for UV or visible light to excite the electrons. But here, it's small enough for UV vis to work. So we use methanol or ethanol because they have only these sigma bonds. So we expose the molecule to UV vis light, wavelength from 200 to 800, and then we see what's happening with that excitation. The light will cause this excitation, electrons to be excited from the filled bonding to the unfilled antibonding molecular orbital. And so we're seeing that excitation and relaxation. So we look at our spectra. So here, spectrum, because we have only one. This is our UV vis. And so with this, we're going to see how the molecule is absorbing this light. As it absorbs the light, it's exciting these electrons, and so we are picking up that exciting of the electrons. So here, 200 to they're only going to 340, but you can go all the way to 800. So here they only had to go to 340 for this, but for this conjugated diene, we end up with this peak here, where we see the highest part of the peak. We would call that lambda max, where that's the wavelength that corresponds to maximum absorption. So absorbance or absorption of that light. So our lambda max, 222.5 nanometers. That's what we get for this diene. So that tells us something. So our lambda max is an indication of the size and degree of delocalization. Our lambda max tells us the size of delocalization and the degree of delocalization of that extended pi system. More conjugation, higher lambda max. More conjugation, higher lambda max. If we get a lambda max of above 400, that's going to give us a compound that has a color. Above 400, a colored compound. So let's look at this table to see this trend. So first we have these non-conjugated. And we see for these non-conjugated compounds, remember, we're going from 200 to 800. Their lambda max is below 200. So we see very low value there because they're not conjugated. But once we get going from a diene that's non-conjugated to a diene that's conjugated, now we can see our lambda max is higher, 217. Going from a diene to a triene, we can see it goes from 217 to 268. Tetraene, 330. Having more conjugation, that's going to increase your lambda max. More conjugation will increase your lambda max. Now let's go back here to this 217. So 217 butadiene versus if we add in a methyl, hyperconjugation plus conjugation. What is hyperconjugation? That alkyl group is donating an electron density, plus we have the conjugated double bonds. So we see that our lambda max is even higher. So hyperconjugation will increase your lambda max. Conjugation and hyperconjugation will increase your lambda max. Something else that will increase your lambda max is having something that is rigid and planar and cyclic. So where are we seeing that? Over here in this part of the table. So we're going to compare our diene, 217 or 225, compare that to 282. So we have a diene here, but it's a cyclic diene. And so for this cyclic diene, rigid, planar, cyclic pi system, we see our lambda max increases. Now look at your triene here versus this triene, 268 versus 324. Rigid, planar, cyclic, increased. We have a tetraene now. So tetraene, 330 versus 355. Again, higher lambda max when we have a rigid, planar, cyclic system. So now we're going from a tetraene to beta-carotene. So beta-carotene is what we're looking at here. Beta-carotene, look at this, 497. Going from 4 double bonds, having all these double bonds in conjugation. Okay, yeah, this isn't cyclic, but we still have a lot of double bonds in conjugation, so 497. That's where we get the orange color. And then here we have 1, 2, 3, 4, 5 double bonds. So not as many double bonds as beta-carotene, but they're all cyclic. Cyclic, conjugated. Here, look at this. A higher lambda max because of cyclic conjugation. And we get this blue-violet color. So hyperconjugation increases, and then having a ring, rigid, planar, extended conjugation, that also increases the lambda max. Questions there? All right, so next week in lab, we're going to be using UV vis to look at beta-carotene and lycopene. So either carrot paste or so carrot baby food or tomato paste, and we're going to isolate these compounds and see what the UV vis tells us about lambda max. So consider this as you were writing up your pre-lab for next week. There's no reaction, so no mechanism for next week. It's an isolation, but we're going to be doing this isolation where we are going to look at lambda max to figure out the conjugation of your final compound. So we'll do some column chromatography to isolate it, and we'll look at that UV vis to see this extended conjugation system, higher lambda max. All right, any questions? No reaction, no mechanism. You're isolating something. You're not going to make beta-carotene. You're not going to make lycopene. You're isolating them. God made them and put it into the tomato and carrot, and you're going to isolate it. Other questions? All right. So, oh, go ahead.
Do you want a reaction table along with the pre-lab?
There's still going to be a table of reagents. Yeah.
Okay, thank you.
Uh-huh. Any other questions? All right, you guys. Well, have a great weekend. I'll be praying for you. Stay safe, stay healthy, and I'll see you guys next week. Love you guys. Bye.